from now on. Okay, and this is another paper similar to LWF, but they are insisting that they are better than the LWF. They have one more distillation loss compared to the LWF. So this is some scenario, what they are doing. So MT-1, this is indicating the task, okay? T-1's task, and this is the T's task, and this is the T+1's task, okay? So they are in T-1's task, they are outputting this amount of class probability, okay? But at this M's task, they are outputting more probability because they have more classes than before, okay? And also in T+1's task, they have even more output, okay? What they want to do is, if they only use the LWF, it is kind of applying some knowledge distillation for this output, okay? Using the network trained in MT-1, they apply some distillation loss for the network trained in this MT phase, okay? And this is applied with the cross-entropy loss, okay? And this is in MT+1 phase is same. They will apply knowledge distillation loss for these old tasks, and this is the new task is applied with the cross-entropy loss, okay? These are same as before, but they are insisting that if they can get this kind of attention using some CAM method, and then they can also close these attentions, the performance will be even better, okay? This is the conclusion of this paper. So, so this is the what LWF is doing. So this is the teacher model trained in previous phase. And here we have more classes, okay? So they apply some knowledge distillation loss for this part, okay? And this is the new tasks loss, okay? But after that, they apply some grad cam method and make some attention map like this. And they also apply attention distillation loss apart from previous knowledge distillation and the classification loss, okay? And by doing this, they insist that their performance is even increasing, okay? And this is the formula that I mentioned. So this is the classification loss, and this is the distillation loss. This is the distillation, and this is the classification loss, and this is the attention distillation loss. Okay, so LWM, this is the kind of LWF plus attention distillation loss. Okay, so yeah, they are insisting that this kind of case, they can capture compared to the LWF, and they are having possibility to be better than the LWF. So this is some sample, okay? So this is indicating the continual learning steps, okay? And if they measure only the knowledge distillation loss, even though their attention map looks like this, yeah, for earlier steps, it can retain the object, their spatial information, okay? Rather well, they can keep the spatial information, but at step N, they can lose the information for the exact spatial location, but even at that step, the knowledge distillation loss could be saved, okay? So from here to here, the model actually loses the spatial information to capture another part of the object, to say that part as that object, but the knowledge distillation loss retains as same. But if we additionally measure the attention distillation loss, at this moment, this loss offers the high loss. Okay, so we can penalize this actually. Okay. So with this attention distillation loss, they are insisting that the model will not lose the spatial information. Okay. So this is the case without the attention distillation loss. Okay. So they are insisting that this attention distillation is important to maintain the information. Okay. So everyone follow this. Okay. It's not that difficult. So this is similar. This is the similar result. Okay. This is the continual learning steps, and this is LWF, and this is the LWM cases. Okay. And this is without any forgetting schemes. Okay. Their spatial information is lost when the continuous learning step goes. Okay. But with the LWM scheme, we do not lose the spatial information. Okay. And another paper introduced for reducing the forgetting is this EWC. As far as I remember, this is elastic weight, the abbreviation for elastic weight consolidation. So yeah, the name is seems like difficult, but their concept is quite simple. So let's say this is the boundary learned for task A. Okay, then your parameters are maybe lying on here, right? This sector A is kind of optimal parameter for task A. Okay. And I mean, good parameters for task A, they are lying on here, right? And good parameters for task B, they may lying on here, okay? And if you train task A first and then do training for the task B, then your network will go here, okay? So here at this point, this parameter sector, like A transfer to B, task B, that we will call it as this. At this location is good parameter for task B, okay? But it's not that good parameters for task A, okay? So here we say the model forgets the knowledge for the task A, okay? So if we use no penalty, it goes like this, and it forgets the knowledge accumulated for the task A, okay? If we penalize the parameters by using L2 loss, so we can do this kind of thing. So we can apply loss for B. This is some cross entropy loss using data from task B. And if we penalize our parameters, this is the parameter learned, and we can maybe apply this kind of penalty for optimizing our parameter sector. Okay, so this is meaning that closing our parameter sector, not deviate anyway, closing our parameter sector to the parameters we obtained from task A. Okay, this is kind of the penalty enforcing not deviated from the original parameter. Okay, and at the same time we apply the loss for the task B. Okay, we can do this, but that will spoil the training. Okay, so it anyways loses the information for task A, but at the same time, it is not that good for task B. So here at this point, this is not optimal point for both task A and B. Okay. So if we naively use this kind of penalty that penalize the deviation from the original parameter sector A on our parameter, new parameter sector, then it goes wrong. Okay. So this paper is proposing this EWC loss. Okay. So what they do is this kind of formula. So it's similar to what I mentioned here, right? They apply LB, which is the loss for task B, okay? And at the same time, they apply some penalization term, okay? This is same as before, right? I is index for all parameters, okay? And this is also same sector star A is the parameter we obtained from for task A, and this is indicating ith element of that. Okay. So anyway, here they have some. Anyway, lambda is some constant. This is constant. We set it like 1 or sometimes less than 1 or so anyway, to balance between this and this, we use lambda. Okay, this term and this term, we use lambda. And the important thing is this Fi. This Fi is the diagonal of Fisher information matrix. And this is actually measuring the importance of ith parameter in sector, okay? I mean the sector I, okay? This is sector I, okay? So it can adaptively apply L2 loads for parameters considering its importance, okay? So this Fi, I mean, how to implement it is maybe you have to refer this paper, okay? But anyways, this Fi, Fisher information matrix, this is related to the importance of the parameters, okay? So if this importance is high, then we will apply more penalty. We enforce more close to their original parameter obtained for the task A, okay? But if this is close to 0, if this is so using this EWC scheme, this is more advanced than the L2 loss, and then we can get parameters which is lying on here, okay? In here, this is optimal for both task A and task B, okay? These parameters are good for both task A and B. So they are insisting that using this kind of scheme, we can get the parameters lying on here, okay? So this is the experiment. So the x-axis, they are denoting the number of tasks, okay? Without any schemes, if we involve more tasks, their classification accuracy becomes low, but using the EWC, it can retain the information and the performance is not that low, okay? And this is kind of the performance obtained for training the model for each data, okay? This is the single task performance. This is kind of oracle. And this EWC, even though they are trained using new task data, their performance is not dropping for the old task. Okay. So this is the result. And another similar approach is also published in ECCB 18, and they are called as memory aware synapses, okay, MAS. So they are also doing the similar thing, having the similar loss function. This is the loss for the new task, and they are penalizing the deviation from the original parameters using some weight, okay? And the way of obtaining this weight is different from the EWC in this paper. What they do is they actually obtain this weight, the importance of parameters by using this. So K is index for data, okay? K is index for data. So for multiple n data, they get this value and they average it and use it as the importance of the parameters, okay? So this, their magnitude is regarded as the importance, and this is actually the gradient, okay? Gradient. So this is indicating that if their performance is changed a lot according to certain parameters, okay? This differentiation is meaning that, so if some models performance varies a lot according to some parameters, then it indicates that that parameter is important parameter, okay? So outputs would be much affected by the certain parameter, then that parameter is important, okay? If their output is not varied by certain parameters, then it means that parameter is not that important, okay? So they penalize the deviation of the important parameters while running the model for the new task, okay? So this MAS is better than EWC and also better than other competitive algorithms, okay? And also the LWF we saw, this MAS is better algorithm. Okay, and another stream of work to prevent the forgetting is the approach called as replay method. Okay, so it's similar to joint training. So, I mean, when we do joint training, our performance was the best, but it requires large amount of memory, and also we our training time is not efficient because we have to supply both old and new data sets to the model. Okay, it takes time. Okay, but in replay method, this is similar to joint training in the sense that it supplies both old and new task data. Okay, so it sees both old and new task data, but they don't have to store this old data in their buffer. Okay, in that sense, they are insisting that this is more efficient than the joint training. So what they actually do is they generate data using deep generative model, such as GAN. So now diffusion maybe. So this method can generate realistic samples from some noise or some conditions. Okay, so what they do here is they are also doing some sequential training, okay? For task 1 to task n, they have to learn some scholars, okay? But they do both things. They involve scholar. This is kind of network we want to train, okay? This is called as scholar. This is the network for the classification, okay? And we involve another network which is called as generator. And actually this scholar, this is the scholar. Scholar is having both generator and solver. This solver is classification network and generator is some deep generative model, okay? So this is the old scholar having both generator and solver. And this is the current tasks scholar, okay? No. This is current tasks data. So here we have input and their annotation here, okay? Input and annotation. This is indicating data. And we have to train new scholar, which is updated from the old scholar, okay? When training the generator for the new scholar, we use only the input X, okay? So for the current X, we can get it from the new data X, okay? For the old X, old image X prime, we generate from the generator, okay? And using these two images, we train new generator, okay? This is the old generator that can generate only the old images, okay? So this X prime is distributed according to the old data, okay? And we add new input X from our new data. And using this tool, we train the generator of the new scholar, okay? And now we will train the solver, okay? So this is also the paired data for new task. And this is the old scholar, okay? And for paired data, from the new data, we can train the solver of the new scholar. And at the same time, for the replayed X prime, we will input it to the old solver to get kind of pseudo label. Then we can get this X prime and Y prime pairs, and we will supply this to the new scholar, new solver, and we'll train the new solver, okay? Then this new scholar is having generator that can generate both X and X prime, and also have the solver which can solve this, anyway, solve the classification for both X and X prime, okay? So this is the replay method, okay? Okay. Kind of we are not using old data, but this generator is generating some images which follows the distribution of the old data, and we can using it to train the new networks, okay? So in that sense, we can say they are using old and new data, but we don't have to say these data in some buffer. So memory requirement, in the aspect of the memory requirement, it is efficient than the joint training, okay? Okay. So are you guys following this? Okay. So this is the experiment. This for the MNIST, they first train the model for the MNIST and transfer it to SVHN dataset. And this is for the reverse thing, okay? This ER means exact replay, okay? ER is meaning they involve. This is actually the joint training, okay? Involving both old and new task data for the training. This is the exact replay in the sense that this generative replay, they are using generated images during the training. So compared to this, they are exact. Okay, they are called this as the ER, and we call this as GR because we are using generative images. Okay. And this is the network trained for MNIST, and this is the network trained for SVHN. Okay, and yeah, this is also the network trained on as the SVHN without any replay. Okay, and this is also the network trained on MNIST without any replay. Then this part we train it for the MNIST, and without replay, the accuracy becomes less. But these replay schemes, they retain the accuracies. Okay. And here the SVHN data anyways looks like this. Previously, this would be almost zero because their data set is different from MNIST. But if they start to train on the SVHN, their performance gradually increased. Okay, and the more important thing is this part. This compared to without replay, this retains the knowledge. Okay. And same as here, this is forgetting, and yeah, yeah. Anyway, they are retaining the knowledge. Okay, compared to this. Okay, this is the experiment. And another stream of the work is so far we saw a lot of categories of work to prevent the forgetting. This is using some generative model to supply generated images during the training. That's the game-based or replay method. And this is using some regularization method during the training, right? So EWC and MAS, they are classified as the regularization method. And this is LWM and LWF, those are distillation-based flows, okay? But here, there are new category. So these algorithms changes the structure of the neural network when the tasks are changed, okay? So this paper is also published in ECCB 18. And what they do is quite simple. So from the input image, maybe they have responses like this. This is not response, but some filter parameters. They may use this type of filters. And also then maybe through these filters, they from the image, they can get some responses, okay? But another thing is here, actually here, from the input image, they estimate some mask weight, and then they threshold it to be binary. So this is indicating 0 or 1 binary, but I mean, directly estimating binary weight, that's not differentiable. So they first estimate some soft values from 0 to 1, and then they apply some thresholding and get this binary mask and multiply these two values to get this kind of on and off filter corners, okay? And their motivation is, according to the input types, they will choose which filter parameters they will use using this mask, this kind of mask responses, okay? And if they train the task A, the patterns for these binary masks obtained from this mask weight, they expecting that their patterns for mask would be different from what during the task B training. Okay, so that's their motivation. Okay, so ideally they are expecting that the mask patterns would be different when training for task A and B, and then they can prevent the forgetting. Okay, so this is the parameters actually used for training. So if the mask pattern is different, the parameters used for different tasks are not intersected, and there would be no forgetting. Okay. And similar, actually, this is the formula again. So previously, this is the weight, and this is the input. This is the convolutional weight, and this is the input, and this is kind of the intermediate layers output. But this time, we multiply some masks, binary masks, having 0 and 1, and multiply it with the convolutional filter kernel, and then multiply with the image input. So this is the new kind of operation they are proposing. And also their mask operator, this is also differentiable, so they can be trained end-to-end manner, okay? And another similar work is published in CVPR 20, and this is called as some conditional channel gated networks for task-aware continual learning, okay? So what they do is also quite simple, and this is the original path, okay? This is convolution neural network, and this is the input feature map, okay? And they output some intermediate output by applying some convolutional network in the middle, okay? But they have another gating network to get this kind of binary masks, okay? And actually their channel number, their dimension is actually same as the channel number of the output map. And they are actually doing this, okay? For the gate output, they multiply this gating binary masks and on and off the output. So here the figure is visualizing that this black is not used, okay? This is 0, this white is 1, okay? So indicating that some channels are not used, okay, by the gating network, okay? So their motivation is also same here. They want to decide which parameters are used, okay, according to the feature map, okay. Depending on the input, they want to on and off the features used for the training, okay. So ideally, if the domains are different, the data they will be appearance, their features would be different, and I mean the same parameters will not be used for those different domains, okay, and there would be no forgetting appears, okay. That's their motivation, okay. So this is the same figures, okay. So everyone follows this. Actually, maybe one of these methods you have to choose, maybe, and also have to implement during the programming assignment too. Okay. Okay. So actually, programming assignment 2 will be announced this week, and that is about these forgetting things. Okay. Okay. So this is several methods to prevent the forgetting, and And we will mention few things about the next topic and finish soon. And more important thing is next Monday, there would be lead presentation for the final term project, right? And you have to send me the 7-minute video, okay, by this weekend, right? So, I mean, you have to remember that I will do this again maybe tomorrow or the day after tomorrow. But anyway, you have to prepare that, okay? So we will watch the video together during the class from next Monday and Wednesday. And we will also have the Q&A session, okay? So yeah, anyway. So here I want to proceed to explaining about the weekly and self-supervised learning method, okay? So far we learned about the pseudo labeling and distillation method, and also any other techniques that can kind of augment the data when the input images are available, right? So by anyway generating some annotations synthetically, that's the pseudo labeling or distillation method. But this is another stream of works that can be used when the labels are not sufficient. Okay, the weekly and self-supervised learning method. So self-supervised learning method, they are called like that because they can learn the model without any tagged data. So actually, they are insisting that even without the labels, they can learn the models. Okay. Maybe I'm expecting that some of you are already familiar with this, but anyways, I will review this, okay? And so this kind of method could be applied to any inputs. When the inputs are available, then we can train the network without any labels, okay? So speech, image, video, text, and etc. We can train them without labeled data. That's the self-supervised learning, okay? And actually, this was proposed in NLP, the natural language processing domain, and when training this transformer architecture, okay? But before that, the self-supervised learning was quite promising, and many vision researchers are also doing that. But I mean, this the architecture called as BERT, but when training this, there requires a lot of language data. But for that amount of language data, it is hard to label it. Okay, so what they do was doing the self-supervised learning, and actually they do two tasks. Okay, masked language model loss and next sentence prediction loss. Okay, so the first one is doing this. So for the input, the man went to blank store. He bought a gallon blank milk. Okay. So in the original sentence, they had the labels for this part. Okay. But they on purpose deleted and make it as the mask and enforce the network to predict that. Okay, that is masked language loss. Okay, they are from the original sentence. They delete some word and make it as the mask and enforce the network to predict that. That is the first task. And another task is actually there are two sentences and sorry, not like that. Another task is there are actually two sentences here, and they have to label they have to predict if these two sentences are next sentences or not. So they already know that these two sentences were together or not. Okay, they already have the labels for that. Okay, because they have the sentence data. Okay, so as they have this word before, they have this. They already know that these two sentences were in the same sequence or not. Okay, they already know that. So if the two sentences were in sequence, they label it as is next. Okay, but if these two sentences were not in sequence, they labeled it as not next. Okay, that's the sentence prediction task. Okay, given these two sentences, the network have to estimate if these two sentences are in sequence or not. Okay, that is the next sentence prediction. So for these two tasks, we already know the labels. Okay, so we don't have to collect more data. Okay, using this kind of solving by solving this kind of sub problem, we don't have to use the collected labels. Okay, these labels could be automatically secured. Okay, so this bird was trained using this type of two problems. Okay, by solving these two problems, the large-scale language model was trained. Okay. So this is an example of the self-supervised learning. And similarly, in the image domain, this type of self-supervised learning was proposed. So when given image, we already know some patches, spatial information. So we already know given these patches, there are patches like this in this location, in this relative location. Okay. So this ICCB 2015 paper, they exploit this prior and train this kind of network. So they insert this, the center patch, and also insert this relative patch here. And they use AlexNet using the same weight. Actually, the weights are shared for this. And they extract some features here, and they concatenate them and map it to some index. And that index is actually meaning their spatial relative spatial location. So when the patches were here, their labels would be 1. And if the patches are located here, then their relative locations are 8. Okay. So that we can secure this kind of labels automatically from our images. Okay. So in image domain, this type of self-supervised signal was already used. Okay. So predict the relative positions of the patch. Okay. And similarly, this ECCB 2016 paper is doing the similar thing, but more they are insisting that this type is more robust. Okay, so what they do is they actually extract 9 patches, and they actually permutate it. So they actually shuffle their locations like this, and then obtain this type of permuted output, and then estimate how they were permuted. Okay, that's actually called as the jigsaw, solving the jigsaw puzzling. Okay, so they are insisting that this solving jigsaw puzzles is better than this relative context prediction task. Okay. Okay. Anyway, this is the architecture for solving that jigsaw puzzling. Okay. And another type of self-supervised learning is estimating the rotation angles. Okay, so this is the original input, but we can rotate it like this. And the network are trained to predict their rotation angles. Okay, and this is called as RootNet, published in ICLR 18. And they are insisting that that's better than jigsaw puzzling or context estimation or other kind of self-supervised tasks. Okay, even though they are simple, they are insisting that that's good for self-supervised learning. Okay, and also there are a couple of self-supervised signals for the video domains as well, but we will learn about this maybe from the next class. Okay, let's finish here. Okay, thank you. 출석 체크 안 하신 분 나오시면 될 것 같습니다. 이름 권소 잠시만요. 네. 안녕. 네, 알겠습니다.